first of all, I should give full credits to this title to Neil Dalal. I stole it from him. A nice talk about intensity interferometry. But essentially, what I want to talk about today is really a continuation of Colin's talk, and in particular, focusing on the idea of how we can use large-scale structure measurements to learn something about BSM physics. So in particular, I want to focus a little bit upon how one would do this, also splicing in a little bit of how we model non-BSM, or SM physics, I guess, and talking about what are the current and future prospects for various different classes of models from current and future generation surveys. So as a brief sort of roadmap of this talk, I'm going to start off by telling you a little bit about what the data is, what the current surveys, what the future surveys are going to look like, and what sort of axes they tend to extend along, a little bit about how we model it, a little bit about what we do with this data, and hopefully finally an extended discussion about what we can learn about BSM from these sorts of data sets. So to start off with, what is the data? So right now, we're really in a pretty exciting time for large-scale structure experiment space. So up until kind of recently, the best data set we've had is the data set from the Sloan Digital Sky Survey, in particular, the BOSS, Baryon Oscillation Spectroscopic Survey, I think, which basically measured about 1 million galaxies across 5 years, culminating in about 2014. And until basically last year, this was the best map we had of large-scale structure. But now we have new observations already have started to come out from DESI. Similar observations are being made from the Euclid satellite, which is this guy over here, which is hopping around somewhere in space. And very soon, we're going to have a whole host of other probes. In particular, the Spherex probe is about to launch, I think, later this year, or even this week. It's super soon. The Rubin Observatory on the ground is already commissioning, and will start doing its science operations very soon, as well as slightly more futuristically, Roman, which is going to be launched in the next couple of years, hopefully, as long as the government don't try and slash its funding again. And then hopefully in the future, we're going to have even more data. So the sort of future plan is something like Spec S5, which is really a very unambitious title, just for spectroscopy stage 5. Also, more fun, used to be known as MegaMapper. For some reason, they went for a slightly more boring title. So most of these experiments are spectroscopic. Some are also photometric. And in general, I'm going to ignore all the photometric surveys in this talk. So I'm just going to be talking about doing 3-dimensional galaxy clustering and not 2-dimensional. Photometric surveys can tell you some additional things, and I'll highlight those a little bit where they're relevant. But this is mostly biased by my own background as a spectroscoper. OK, so what do these surveys actually measure? So in general, spectroscopic surveys try and measure the distribution of galaxies as a function of both space and time. So this kind of infographic here, which I think might be Claire Lammons, or at least the DESI publicity teams, actually shows kind of what you're trying to do. You're trying to make a map of every single galaxy position seen by a telescope. This is not to scale. It'd be kind of cool if it was. And also, these galaxies are not this color, but these kind of demarcate a couple of different redshift regimes, which I'll talk about in a second. And in terms of scale, some of these surveys have very different physical manifestations. So they range from ultra-large surveys. So for example, Spherex is designed to measure essentially the whole sky. And other surveys, like the Roman telescope, is trying to measure things ultra-deep. So they're focusing on a very small area of the sky and trying to measure it at very high depth and very high precision. And which survey you should be interested in really depends on what your targets are. So if you're interested in large scales, you're probably going to be looking for things like inflationary physics or relativistic corrections, other sorts of Einsteinian effects that could impact those sorts of scales. Whereas on small scales, the focus really changes to nonlinear stuff, as well as galaxy formation. So altogether, LSS surveys probe a really wide range of scales. In Fourier space, it goes down to about 10 to the minus 4, just about, all the way up to about 1 H per megaparsecs, which is roughly speaking about a factor of 10 smaller than the CMB. So CMB beats us on ultra-large scales. We have a little bit more small-scale dimensions. And some surveys do go deeper than this. For example, cosmic shear surveys and Lyman alpha surveys can extend this up to about K of 10, K of 100. So in terms of the time axis, we also have quite a lot of variability. This is where a large-scale structure is nice. We have this extra axis to play with that we don't in the CMB. So some of the surveys are ultra-low redshift, down to like Z of 0.1. Some of the surveys go much, much deeper. In particular, some of these future surveys like Spec S5 are going to really try and push this up to like redshift 4, 5, or 6. So once again, these are good for different things. Low redshift galaxy surveys tend to be magnitude limited, so they can basically probe all galaxies up to some magnitude cut, which is good if you care about nonlinearity stuff, galaxy formation, etc. Whereas the high redshift samples are very, very sparse usually, just because it's a lot harder to form a galaxy at high redshift. They're a lot rarer, but they tend to be a huge volume. So they're really nice for probes of primordial physics and inflation in particular. So of course we can learn more about things by combining probes. Colin mentioned this a little bit more. We heard more discussion of this earlier with things like patchy screening. We can combine with, for example, cosmic shear, CMB lensing, or some of the other fun CMB secondaries, like the thermal or kinematic Sunyaev-Zeldovich effects, or even some probes of gravitational waves. A nice thing about this is that essentially you're combining your information in the galaxy surveys with traces of other stuff. So whether that's the distribution of dark matter, even technically lensing potentials, or the distribution of baryons or hot gas in the late universe. So that's all the data. But how do we actually make use of this in practice? So in terms of the theory, I kind of like to split things up into about 4 different regimes. So the first regime is the initial conditions. So everything we see today comes from inflation, or your favorite theory of the primordial universe, which essentially, for our purposes, just sets the PDF of the primordial curvature perturbation as zeta. The next thing that happens is we turn inflation into the early universe. We have a whole bunch of fun radiation physics, which also sets the CMB. For our purposes, this sets the power spectrum of dark matter, in particular, the linear power spectrum. This guy then expands, and the universe expands and grows, both in the background and in the perturbations. And finally, we have all the fun nonlinear problems that we have to deal with. For example, formation of dark matter halos, galaxies, etc. And the reason I point these out is because each one of these different themes can really tell us about some very different types of BSM physics. So how do we go about doing this in Lambda CDM? So for a second, let's assume we don't have any BSM and just think about the basic thing. So in terms of the initial conditions, this is relatively easy. We assume that the initial conditions are Gaussian, scale invariant, and adiabatic, or more specifically, that the primordial PDF can be described only by its 2-point function. So we don't have a bispectrum, don't have a trispectrum, etc. And that this 2-point function is almost scale invariance, described by some amplitude, AS, and some slope, NS. And the idea here is this NS is slightly less than 1, giving us the standard slow rolling inflation. Adiabatic's also interesting. This basically means that every field I could be interested in, whether this is baryons, dark matter, or photons, they each share the same initial conditions. Essentially, there's only one field in my early universe. In the early universe physics, we then have to start thinking about the standard radiation transfer and fun things like that. And in this case, there's basically 2 main things that happen. The first one is we have changes to the expansion history. So we start off with a universe that is dominated by radiation. And by around redshift 3500 or so, we end up with a universe which is dominated by dark matter. This is conventionally parameterized by this equality scale, K equality, which is a very strong probe of cosmology. In particular, it's proportional to the matter density times by h naught, the Hubble parameter. In fact, this is the original probe which large-scale structure was designed to try and measure back in like the 1980s or so, originally called the gamma parameter. Early universe physics also tells us a lot about recombination, particularly including the sound horizon. This is sensitive to a different set of cosmological parameters. In particular, we care a lot about the physical densities of dark matter and the physical densities of baryons. Next thing we have to worry about is this growth. So it's generally useful to split this into 2 pieces. Number 1 is the growth of the background of the universe, and number 2 is growth of the perturbations. The background is kind of easier. It's just set by what stuff is there in the universe. In particular, what is the energy density of any species I care about, whether this is the energy density of dark matter, of radiation, of dark energy, or any other component you put in the universe. And when we start thinking about the perturbations and how structure grows linearly with time, we then have to start adding in a little bit more information about GR. Finally, we have to do the nonlinear bit. And this is really the tough bit. This is the reason why Colin says that large-scale structure is less robust than the CMB, which I totally agree with. for the record. It's much harder. And in this case, we really have to worry about all of the extremely hierarchical nonlinear stuff that happens. So I want to emphasize this a little bit more and to tell you a little bit more about how we model this in general, because it sort of underlies all of how we actually get out any information from large-scale structure. So the sort of modern approach to doing this splits the problem into two stages. The first thing we do is we take the primordial universe and we evolve it down to redshift 0 and consider only dark matter. So essentially, you can see this on this plot here. Like this is the primordial field we see in the universe, and at the bottom is the matter field. This comes from the Quixote simulations. There's multiple ways to do this. So generally, it can be done numerically with simulations. We have some simulation experts in the room here. But it can also be done analytically. Now, I'm a theorist, so I'm mostly going to talk about the analytical stuff here. And indeed, this is the way that a lot of the current spectroscopic surveys are actually tending to treat the data. One of the main tools for this is known as the effective field theory of large-scale structure, which is essentially an analytic model to connect between primordial and late-time universes. And an important feature of this theory is it involves smoothing. So essentially, we say the universe on small scales is extremely chaotic, it's extremely nonlinear, and extremely hard to model. And as a result, we can't model this using analytic techniques. So what we'll do is we'll simply apply some smoothing operation to get rid of all this small-scale stuff that we can't hope to measure. In particular, we convolve our true theory with some smoothing kernel depending on some smoothing scale, which is typically around 10 megaparsecs. This is important because it essentially means we have no predictive power beyond that. We're just getting rid of all those information. So once we've done this, then this is a lot easier. Things are, instead of being horribly nonlinear, they're now quasi-linear. And we can easily write down some kind of perturbative ansatz for what my distribution of dark matter should look like. So very schematically, my dark matter at leading order just traces the initial conditions. You can kind of see that from the plot here. Like regions with most dark matter also have most inflation. That's great. But then we have to have hierarchical, higher order corrections, quadratic, cubic, etc. The nice thing about this is that the couplings of the theory are completely set by gravity and GR. And it also comes with a whole bunch of free counterterms, or Wilson coefficients in formal EFT speak, which account for all the small-scale stuff in the model we got rid of. In particular, the action of this coarse graining operation. So these guys are generally fit from data, and they account for any small-scale physics that can happen. For example, gas being expelled from galaxies. Formally, this is equivalent to renormalization. So I should say, this is of course only one way to do this. You could also do everything here with simulations and end up just emulating some kind of statistics of your dark matter at the end. Produce some more fancy machine learning prediction for the field itself, rather than a statistic. So this is part of the story, but we of course also have to match this down to galaxies. So in reality, we see kind of this discrete map traced by galaxies instead of the continuous dark matter field. So we need some kind of analytic, semi-analytic, or numerical way of relating the two. So once again, I primarily tend to work analytically. So within effective field theory, we essentially do this just based on some symmetries. So we're going to take a very similar approach. We're going to say, well, let me take this galaxy density and write it perturbatively in terms of the dark matter density. This is the only field it could depend on at leading order. So we'll just write down every possible dependence we could think of. So for example, this is kind of the full relation here. I'm having trouble with this mouse today. You can see that at leading order, this is better. Leading order, the galaxy density depends linearly on the dark matter density. And then we could basically include a suite of higher order terms. For example, we could have it depending quadratically. It could depend on the tidal field constructed from dark matter, or the derivative operators, et cetera, et cetera. And in general, this form of this expansion is completely defined by symmetries. In this case, the symmetries we have are symmetries of homogeneity, isotropy, and Galilean invariance. And it involves all of these different operators we can write down, plus some number of free coefficients. And the free coefficients here are essentially the responses of my theory, or more technically, the bias parameters. So these guys basically just say, what is the correlation coefficient between galaxies and dark matter? They're something that depend all on galaxy formation physics, and a priori, we can't predict them within the theory. So this is a nice approach. It's very robust, because we've basically listed everything that could happen by symmetry, it is complete up to the scales that, up to a specific order of this Taylor expansion here. It contains every information we could care about, but it is essentially limited. We've done this smoothing, we've got rid of some information, and we've also encoded all these bias parameters which encode all sorts of small-scale fun and said we don't know anything about them. So essentially we are always losing information with this sort of treatment. But we do that at the expense of being robust. Of course, there's other things we could do. People these days are getting quite interested in doing these things with simulations, at which point we basically model the dark matter field, and then right at the end, we try and find some kind of semi-analytic connection between dark matter and galaxies, whether this is with a halo occupation distribution or some kind of semi-analytic approach. Or of course, we could go ahead and do the full thing when we just predict my galaxy field from scratch with some kind of hydrodynamical simulation. This tends to be extremely expensive if you're trying to do it on the full scales of a galaxy survey. Okay, so once we've done this, we then have to compress down to some kind of statistic. So most, to date, basically all analyses of galaxy clustering have focused on one of two statistics. The first one is the baryon acoustic oscillations, essentially the late time manifestation of the sound waves from inflation, sound waves from the early universe. This is a really nice probe. It's very good for tracking the expansion history of the universe. Essentially, we have this fixed scale in the universe, which expands with the universe, and we can measure. But of course, this isn't the only information we have. In the same way as in the CMB, we can really measure the whole two-point function. For example, this is the power spectrum that you measure. In fact, this is from legacy galaxy survey data. You can see it has a lot of information in it. It has these BAO features, which are little wiggly bits here, which you can only sort of just see on this plot. But it also has a lot of other features. There's information in the amplitude of this thing, there's information in the height of the wiggly bits, et cetera, et cetera. So this is kind of the main statistic that now large-scale structure surveys have started to use. Like this was the main point of the latest DESI release, was to analyze this guy in full generality. And Euclid similarly will do most of its analysis based on the power spectrum. But there's really a lot more you could use. So other options that you could be interested in, and I should state here that the statistic you care about really depends on the physics you care about. But another option would be the bispectrum or trispectrum, essentially tracing the 3 or 4 point functions of galaxy surveys. So this inherently is nonlinear and it's non-Gaussian. And this is very good if you want to trace, for example, the 3 or 4 point functions of inflation. Just at leading order, those two things are going to correspond to each other. However, this is hard. It is expensive, it's hard to compute, and it's hard to analyze. So I think a general sort of takeaway that we've sort of seen in the last couple of years is that you should probably only be analyzing 3 and 4 point functions if the science use case you want depends on doing that. There's a lot of other probes. For example, we could look at halo-based information or information on very small scales, for example, galaxy bias. This can be actually quite a sensitive probe of a lot of different varieties of new physics. And in particular, it's sensitive on physics of scales down to the sort of characteristic size of the dark matter halo itself, down to about sort of 10 or even 1 megaparsecs. This, in general, is very difficult to model. Similarly, there's been a whole host of nonlinear statistics proposed: wavelets, k-nearest neighbors, convolution neural networks, marked statistics, density split statistics, reconstructed fields, et cetera, et cetera. So these are potentially really nice nonlinear ways to reconstruct some of the non-Gaussian information imprinted by nonlinear clustering, for example. But in general, these do have to be modeled numerically. They're quite difficult statistics to track analytically. Furthermore, there's other things we could look at. For example, cross-correlating my galaxies with weak lensing. This is actually a really nice probe of gravity, because weak lensing is directly probing the potentials of the universe. Or cross-correlating, or even using directly information in the spins of galaxies or the shapes of galaxies. Once again, this is a probe of weak lensing, but it's also a probe of some interesting higher-order physics, for example, including vectors and tensors in the universe. Okay, so putting all this together, essentially, the point we're at right now with large-scale structure is that we have codes that can essentially evaluate all of these different theory things very, very quickly. So right now, there's about 6 or 7 different codes that will do this for you. The point is, you put in some cosmology parameters, you run the code for like a second generally less, and it spits out some models of the power spectrum, which you can then fit to data. These include a whole bunch of additional things you need to use in order to compare to realistic data, like the effect of the survey geometry, the mask, redshift space effects, etc., which are less important for our discussion here. The point is, by combining these models with some kind of likelihood, normally assumed to be a Gaussian, plus an observational data set, we can essentially constrain any parameter that enters the model, pretty much in exactly the same way as we do in the CMB. They've been used to measure a whole bunch of cosmological parameters. For example, this is some of the recent DESI results. You can see we measure omega matter and sigma 8, and we get some constraint, which looks like Planck. That's great. The most interesting thing here is how we can do this for models beyond lambda CDM. And in general, there's two avenues we need to open up here. First of all, we need to check if our theory model still applies beyond lambda CDM. And secondly, we need to work out if the statistic we're using is the right one. Like what statistic is best for what type of new physics. And in these sorts of avenues, working with theoretical models is particularly useful instead of working with, say, simulation-based treatments, because new simulations are expensive. Ideally, we don't want to have to run a 1,000,000 CPU hour simulation every time we try out some different model of new physics. So how do we actually go ahead and model this stuff? So this was the slide I showed you before. Essentially, how do we model a galaxy survey in lambda CDM? And a good roadmap of everything that we could do with BSM is essentially just looking at these assumptions and breaking each one of them in turn. So we can modify inflation. That will show up in a galaxy survey. We can modify physics in the early universe, which changes the linear power spectrum. We can change the expansion history. And finally, we can change the formation of structure in the late universe. And for the remainder of this talk, I really just want to talk about each one of these avenues in a little bit more detail. So the first one is the initial conditions. So before, I said the initial conditions are three things. Number one, Gaussian. Number two, scale invariant. And number three, adiabatic. We can easily break any of these assumptions. And a simple thing we can do is essentially just to change this power spectrum. We said that the galaxy density is sensitive to the initial conditions over very wide ranges of scale. So we could change this power spectrum in any of that wide ranges of scale, and we'd expect to see it in the data. So an interesting way to do this is with something like primordial features. So for example, if I take my power spectra with its usual almost scale invariant form, I could start adding on things like oscillations, for example, cosine of the log of the scale, or just cosine of the scale. This is kind of a plot of what this would look like. This gray line running along here is the usual power spectra, and then the blue and the red are two different types of oscillations, which could be produced via different effects. For example, axions in the early universe with a periodic potential, or some kind of resonances, like particle production at one period of time, some fun stuff like that. These guys produce a change to the power spectrum, which of course then produce a very similar change in galaxy clustering. Essentially, we'd be looking for a galaxy power spectra which had a very similar oscillatory feature in it. We could also change the scale dependence. Instead of having this simple 4 minus ns, or ns minus 4 slope, we could start adding some scale dependence to this. For example, this spectral running approach, when we add kind of a log k correction to this thing. This is really a nice probe of the inflationary potential. And this spectral running is actually produced even in the standard, simplest vanilla models of inflation, but its amplitude is usually indetectably small. It scales roughly as ns minus 1 squared, which is like a factor of 100 smaller than the constraining power, and thus will probably not measure it, at least in the next 10, 20 years. But a whole bunch of interesting models can produce this, particularly things beyond single field inflation. So any detection of this would be a real smoking gun of new physics. Okay, another thing we could do is break the assumption of Gaussianity. So as we heard about this morning, there's a lot of interesting primordial physics going on from, for example, inflationary bispectra. These guys can be sourced by just the standard inflationary field interacting with itself, some kind of single field self-interactions, such as those described by the effective field theory of inflation, which are generically written in terms of the FNL equilateral and FNL orthogonal amplitudes, which essentially probe different coupling terms within the EFT inflationary Lagrangian. Furthermore, as we heard a lot about this morning, we could learn about inflation with extra fields in the problem. We could have extra light fields, which translate to F and L local, or extra fields with mass, spin, etc. We could also do the same thing with inflationary 4-point functions. These essentially probe very similar regimes. We can probe self-interactions with inflation, as well as a whole host of different extra fields. In this case, the 4-point function can actually add a little bit more information that you wouldn't see in the 3-point function. In particular, it can probe some statistics like chirality, as well as some really general regimes of the cosmological collider. A classic example of this is, imagine, for example, I had one of these primordial particle exchange diagrams we heard about earlier, and I had a spinning field in the middle. The 4-point function can essentially probe this spinning field with every different helicity state, whereas the 3-point function can only probe just the longitudinal mode. It can only probe one of the helicity states, just based on symmetry. So this is a really nice kind of inflationary spectrometer to probe both the mass and spin of new Hubble scale physics going on. We can also do some non-perturbative things. For example, we could take the curvature and add some kind of logarithmic correction, changing the PDF very strongly. Like this is a plot of the standard PDF here. Oh, this is weird. Anyway, yeah, this is the standard Gaussian PDF of inflation. There are certain models that predict, for example, heavy tails, where this sort of, for example, this red PDF here extends to much rarer events than normal. That can be predicted, and it can give us some corrections not just to the power spectrum and the bispectrum and the trispectrum, but very high-order statistics. And Colin told us one example of this earlier, sort of extremely heavy massive particle production. We can also probe new fields entirely. In particular, we could probe isocurvature. So multi-field inflation can often produce an extra kind of degree of freedom during inflation. Some topological effects can also do this. So these guys may not be correlated with a standard curvature perturbation at all, but they can leave additional signatures in the early universe, which could show up in late-time statistics. Like this is just kind of a little plot to demonstrate this from Alex Barrera. This is the usual, I need to stop trying to use this. This is the usual power spectrum in blue of galaxies here. And this little enhancement in blue is what happens if you add some extra isocurvature contributions. Don't worry about these other lines, they're kind of higher order contributions. You can see at leading order, this produces a massive enhancement on the ultra large scale power spectrum. In particular, this is coming from galaxy bias relating to this extra field. Essentially, galaxies forming not just in response to the curvature, but also this isocurvature mode. Some of these effects could be hidden in the CMB. We can also probe things like tensor modes. So in principle, inflation could produce both scalar and tensor fluctuations. These tensor fluctuations could be correlated with the scalar ones, or they could be uncorrelated. And these do leave some signatures in large-scale structure. In particular, they tend to leave signatures in the shapes of galaxies. Essentially, you have a spin-2 tensor from inflation, and galaxy shapes are also a spin-2 tensor. But I should say these signatures are generally really, really weak, which is a bit of a shame, but in principle, you could detect them. Okay, so why do we actually care about this? Well, this is interesting because it impacts the distribution of galaxies in multiple ways. So the simplest way you can think of is just linear evolution. So essentially, new physics in this curvature directly impacts new physics in dark matter. But the problem with large-scale structure is that we also have to worry about higher order corrections. For example, we have second and third order pieces in this Taylor expansion here. So in general, it's not quite the simple scenario we have in the CMB, where, for example, a bispectrum in inflation leads to a bispectrum in large-scale structure. In large-scale structure, a bispectrum in inflation leads to both a power spectrum, a bispectrum, a trispectrum, and beyond, which is a little bit more painful to model, but can be done using very similar techniques to what I mentioned before. We also have to worry about changes, for example, to galaxy bias. So this is kind of a very old plot now, but a nice plot about how galaxy bias changes in response to primordial non-Gaussianity. An important thing you see here in the red curve here is that on very, very large scales, on very small scales, nothing happens at all. But as you get to larger and larger scales, or lower and lower k, you get this massive uptick in the effective bias of galaxies. This is essentially caused by light fields in inflation modulating how galaxies actually form in the late universe. This sort of famous 1/k² divergence. So typically, we try and constrain all these things using lower order statistics on large scales. This is mostly a limitation because of theory, because of how we actually model these things in practice. But we could hope to learn something slightly more with other statistics. For example, trying to measure primordial non-Gaussianity from wavelet statistics or something like that. Or trying to add in more information from small scales. There's some interesting approaches that we could use to do this. For example, some small-scale signatures are protected, for example, by particular symmetries of the universe, such as the equivalence principle. And in some cases, we can kind of get around these limits of not being able to have a good model just by invoking these kind of symmetries. And talk to Sam Goldstein, or Lam, or Colin, if you want some more information about some of the recent things we've been thinking about in this sort of avenue. So an interesting point I should make here is, well, why should we do this? So Colin's just told us that the CMB is great, and I agree. But why should we go ahead and look at large-scale structure? And it is true that pretty much every inflationary signature you can think of also shows up in the CMB. And right now, the CMB dominates the primordial information content that we have. Like, the CMB is very high resolution. We can go down to L of 2,000 or 4,000 or 6,000 very soon. And you can see in this kind of plot here that this is a plot of the amount of information in a given survey from a primordial standpoint. And Planck is this red dashed line here. Like, you could think of this technically as the number of independent modes of inflation each survey measure. And the current generation of large-scale structure is this green dot down here. So if you take one thing away from this plot, it's that galaxy surveys really suck at measuring inflation. But this situation is gradually changing. In the current decade, we're moving from the green blob here to the orange curve, which gets deeper along this axis, but also more and more information. And in the next decade, we're going to get significantly more information from galaxy surveys. For example, we're going to go over to this kind of blue line just skating up here, which would be an early forecast for the SPEC S5 experiment, for example. You can see that we're beginning to beat Planck just on a mode counting perspective. Essentially, these surveys see more of the universe. And moreover, we're beginning to beat any future CMB mission. Essentially, the idea here is that future CMB does become limited by the two-dimensional features of the CMB and a lot of the sort of foreground and other effects that we have to deal with on the CMB in very, very small scales. There's also a couple of more model-specific approaches for which large-scale structure could be very, very useful. For example, the CMB is a two-dimensional field, and it's integrated over the third axis. And if you have any very small-scale features on the CMB, these features can be washed out by that integration. This is true, for example, some of these primordial oscillation models and oscillatory features in the power spectra. Furthermore, there are some effects that simply vanish in the CMB at leading order because of its geometry. For example, some kind of chiral couplings can be killed at leading order in large-scale CMB, but wouldn't be killed in large-scale structure. Furthermore, the CMB is primarily a probe of photon anisotropies. The polarization is a little bit different, whereas the large-scale structure is a probe mostly of dark matter. So you are probing different things, which is important, for example, in some of these isocurvature studies. So now talking a little bit about the early universe, there's a lot of other interesting things that are active in the universe at very early times. For example, early dark energy. This would be some kind of modification to the growth history, like redshift 100, all the way up to about redshift 10,000, which Colin showed this plot of earlier, which comes from his paper. This is basically kind of easy to model in large-scale structure. All we need to do is just change the input power spectra. We said all the new physics comes from changing dark matter at high redshift. So that's all we have to do. We just run exactly the same code, exactly the same analysis pipeline, just swapping out one power spectrum for another. And that allows us to model any time of interesting new early universe physics, whether that's primordial magnetic fields, early dark energy, models of light relics, self-interacting neutrinos, electron mass variation, etc., etc. As long as the effects only happen early, we don't have to worry about any other complications. So phenomenologically, these effects generically lead to changes in some of the different features we see in the linear power spectrum. So a couple of things we could think of happening. One of them would be a shift in the peak of the power spectrum. For example, this is a plot of the log power spectrum. You see some peak here, which is set by the transition from radiation domination to matter domination. That guy can shift in the presence of new physics because of extra sort of energy injections, for example. We could shift the position of the BEO position. This would come from changes in the sound horizon. Or we could shift the phases of the BEO. We could shift the damping of the BEO. Or we could suppress the whole power spectrum on small scales. So that will be an example on the bottom-hand side here. We're seeing that this is for axions, for example, from Keir Rogers' paper, that without axions, we have a power spectra extending down to very, very small scales. But once we start adding in very high mass axions, we can get a huge amount of power spectrum suppression. So a lot of these models have already been constrained. They're pretty easy to do so, and thus the community's been able to get behind and do this. And many of these constraints are comparable to the CMB, but do have a couple of advantages. In particular, they can reach smaller scales. Like, for example, with axions, this is very clear. You have that sort of extra order of magnitude sensitivity to scale, and thus to mass. And in general, it's been shown many, many times that these effects can break parameter degeneracies present within the CMB, and the combination of CMB plus LSS is much more powerful than any in particular. Okay, so two last things. First one is the expansion history. So large-scale structure is inherently a tomographic probe of the universe, and baryon acoustic oscillations in particular are a really nice geometric probe of the universe. So they're probing any changes to the expansion history over time, in particular the late times. This is a plot of essentially the size of the universe as a function of scale, normalized by a whole bunch of stuff. And you can see we get some nice plot. And essentially all the data points look roughly similar to the theory, which is good. This is a really nice probe of the curvature of the universe, because that sets some of this expansion history. It's also a really nice probe of dark energy. So people like to model this kind of semi-phenomenologically to say we've got some kind of effective W0, WA parameters, and then try and go ahead and measure them, see if there's anything that doesn't look like dark energy. Now, we can talk about this more in the discussion later, but from this nice plot of the matter density against this overall equation of state, so essentially ignoring this equation, but just saying the equation of state is a constant, you can find that everything looks exactly happy and normal. Galaxies are this blue curve here, CMB is the purple one, and once we pop everything together, you get a really tight constraint on both of these parameters, breaking the degeneracies present within each of them. But once you start adding in extra parameters, in particular time-varying dark energy, there's some indications that things might be going a little bit awry. But yeah, maybe we can discuss those a little bit more later. So, finally, we can also measure perturbations and the growth of perturbations in the universe. This is kind of a slightly different probe. It's no longer background. It's now a higher order effect. Within large-scale structure, this can be a little bit difficult to probe. Essentially, we're trying to measure the amplitude of the power spectrum, but we have to take into account the fact that there's a whole bunch of other amplitudes we also don't know. For example, the amplitude of the galaxy power spectrum is not just the primordial amplitude, it's also modulated by the galaxy bias, all the uncertainties about galaxy formation. But there's a bunch of other effects that come into play here. In particular, galaxy power spectra are also sensitive to the velocities of dark matter through redshift space distortions, essentially add dependence on the derivative of the growth rate, as well as some of the higher order effects. For example, damping of the baryon acoustic oscillations and the amplitude of higher order loops in the power spectra directly trace this growth factor itself. So this is a nice probe of anything that changes gravity in the universe. For example, there's this nice prediction that f of z should just be basically the amount of matter in the universe to the power of 0.55 with GR, but modified gravity can in general break this, as well as other combinations of probes as well, but I'll skip those for now. So the late universe physics is really when all wild stuff can happen. So this is, as I said before, the hard thing it is to model, and that also means it's the easy thing to modify with any new physics you can think of. For example, dark matter. So you could very easily change your model of dark matter, adding warm dark matter, fuzzy dark matter, self-interactions, decaying, etc. And these guys have an interesting effect on large-scale structure with a suppression of LSS or an enhancement on a characteristic scale set by their mass. And this is a really nice probe because a lot of these things can't really be seen in the CMB because there are a lot more late-time effects. And they can benefit from extremely small scales, like actual knowledge of the halo profile as well as, for example, Lyman alpha. Finally, we can also look at things, for example, scattering and decay and the dependencies of all the different contributions to our cosmological model. For example, there's been a lot of recent work thinking about scattering between dark matter with dark radiation, or dark matter and dark energy, or dark matter and baryons. And this sort of interplay between different scales can really importantly affect clustering at very, very late times. So this is actually a nice plot from Alex Leguay. You can see this is a plot of the change in the power spectrum induced by some of these scatterings. An important thing to note here is that the linear prediction, which is essentially a suppression of the power on some characteristic scale where this scattering is important, the linear effect is extremely different to the nonlinear effect. It's like a huge amount of nonlinear enhancement of these sorts of effects. And in general, this can be a bit of a problem. If you have some kind of new physics in the universe which is important on late times, it is no longer sufficient just to try and model it by changing the linear power spectra. In practice, you need to start everything from scratch. You have to recompute the whole perturbation theory, and it's a lot harder to analyze in practice. And there's been a lot of sort of interest in these sorts of things, but in general, this is where large-scale structure could be really useful, but it's really, really hard. So I'm essentially running low on time. I'll just say the other fun things are baryons, great, these are fun. It's technically beyond standard model because standard model, I don't know, most simulations don't have baryons on, so that's kind of fun. Fifth forces, etc. I think Diego will probably tell us more about these sorts of things. But yeah, what's next? Well, we're sort of in this regime where we've developed a lot of tools to learn a lot of BSM physics from large scales, but the nonlinear scales and the smaller scales are really going to be challenging. These scales cannot be modeled perturbatively, and perturbation theories, even when they are valid, lose a lot of information because of all these small-scale stuff we've integrated out. So I think an important question for the future is how can we do better? Like, how can we make use of small-scale information whilst remaining robust to galaxy formation? And that is very important. We don't want to accidentally detect new physics simply because we didn't include all the possible things that could happen with galaxy formation. So next generation surveys are great, and I'll finish by saying thanks.
Thank you, Oliver, for that great overview. Do we have questions? And please please remember to use the mic that's in the front of your seat.
So you showed that primordial figure of merit for CMB and current surveys, and then I failed. And Spec S5. Does that just like immediately extend to any other like non-primordial physics, like the late time physics that you were just talking about?
Yeah, so I think late time physics in general, large-scale structure becomes significantly more useful. It really depends on what you're looking for. Like you can imagine having some kind of probe of new physics that affects just the perturbations at redshift, I don't know, 900. Then the primary CMB is unaffected. You can, of course, see things in CMB lensing, but anything like that, large-scale structure just becomes way more powerful. So I would think of that generally as more of a lower bound in terms of actual late universe models of new physics.
And I guess with Spec S5, there's going to be a gain from earlier times. The nonlinear scale is slightly smaller, and I don't know if that's actually all relevant.
No, that's really important, actually. So for Spec S5, you're hoping to be able to push down to like K of 1, still in the quasi-linear regime, which the increase of signal to noise with K max is very large. It goes as K max cubed, which is essentially really powerful. So we'd love to be able to extract the information. With Spec S5 and high redshift surveys, we do have the problem of how we treat galaxy formation at these high redshifts. And even though dark matter nonlinearities become small, it's less clear whether galaxy formation nonlinearities are also small. I think that's a very active topic of investigation at the moment.
Cool. Exciting, thank you.
There are recent claims by... sorry. I always fail with this speed. Okay. There are these recent claims by Misha Ivanov saying that the same EFT machinery can be applied to Lyman alpha. Can you... I mean, in principle, with, of course, like much wider gain for BSM, no? So
yeah, so I think it depends what what Lyman alpha you're using. So I mean, the Lyman alpha tends to divide into two camps. There's a camp that does extremely high resolution experiments on very few sight lines, and ones that do lower resolution experiments on a lot of them. I think the stuff Misha's been looking at is mostly the second camp. It's when you have a lot more sparse sample, and Kmax for him I think is around sort of 1 or so, which is not crazy given that at this point you're at high redshift, like redshift 2 or so. So it's still relatively linear at these scales. Lyman alpha does have problems because you no longer have this nice free velocity field. You break at isotropy, which means you have significantly more bias parameters, and there's a lot more information loss because of just galaxy formation uncertainties, or in this case, Lyman alpha uncertainties. I think it's possible. It's unclear how much it will be useful, I think.